Everybody. Our guest speaker today is Professor Raşit TURAN from Physics Department. Professor TURAN received BS and MS degrees from Middle East Technical University and PhD from Oslo University. Now he is the director of GUNAM. He is going to talk about GUNAM this afternoon. And he is the author of several publications. He has FP6 and FP7 projects and several graduate students worked with him. I'm not going to list all of them. I would like to terminate this brief introduction with a statement from Sour Times, Ekşi Sözlük. Güneş Enerjisi Araştırma ve Uygulama Merkezi'nin kurucusu ve müdürü, güneş enerjisi HES'ler kadar yatırım yapılmaya değecek hale geldiğinde 500 TL'nin arkasında resmini görebiliriz. Okay, it's yours. Thank you very much for joining us.
Thank you for the nice introduction. It's very nice to be here. I have several other statements in Ekşi Sözlük, but I don't want to mention all of them. So some of them are not quite nice. Some of them. Okay. So very nice to be here. So I have several students from this program, from the OYT program, and I'm very happy with all of them. They are working in my group. It's our center towards their degrees, for master or PhD degrees. And I hope that some of you, at least after this seminar, choose this field as a field of your career or your future, because this is a really very interesting field in terms of both scientific studies and also industrial applications. If you want to be a faculty member or a researcher in an academy or in a research center, this field, I think, is one of the best ones, I think, for your future. So you may interrupt my talk at any time you wish, so you can ask questions. So I really like to speak interactively with you. So if you have any questions, just interrupt my talk and ask me. Okay. So I am, as stated in the introduction, I am the founder and the director of Center for Solar Energy Research and Application. And I am faculty member at the Physics Department. Today I will be talking on photovoltaic technologies, energy technologies, but most of my talk will be on our centers. I will give you more information, what we are doing, our laboratories, our students, our research projects, so you get an overview of what we are doing here at TURAN. But before that, I have a very short introduction on energy issue, because energy is the very hot issue today for all societies, all nations in the world, especially for us, because of for many reasons, because of economical reasons, because of ecological reasons, because of political reasons. Energy is the central issue in this country, so we have to deal with it, and we have to solve the problems related to the energy. Okay, let's see. Ahmet? Okay.
I can do it for you if you like.
Okay. When we look at the energy demand in the world, as you might guess, it is increasing. And today, we are around this point. Total energy consumption Okay, the total energy consumption is at around 18 terawatt year. Okay, so you multiply terawatt 1 year, so you obtain this value. This is the amount of energy that we are using today in all different types, including heating, including car, transportation, production, electricity, etc. So, and you see that this is increasing, and we will reach this value in about 15 years, which shows a significant amount of increase. So we have to find a huge amount of new resources to provide our society with this much energy. Okay, so this means huge amount of investment, amount of money. This means huge amount of disturbance in the nature. So it's really very high. And interestingly, and you may also anticipate this, the developing countries is increasing faster than industrial countries because developing countries, they are developing. So it means that they are investing more, and they are growing. So they are putting more money into the energy sector. Okay, just to understand what these numbers mean, you can look at the Turkish total energy demand. Today, Turkey is using this much energy in a year, which is about 1% of the total world consumption. So we are using about 1% of the total energy the world is now consuming. Okay? And new energy demand that we need to find and we need to provide in 20 years, in 15 years, is about 40 times Turkish today's consumption. So we have to create 40 times what we are consuming today for the next 15 years. Çalışmıyor. In order to generate this electricity, we are burning, we are burning whatever we find around us. We are burning coal, we are burning oil. Okay, so this is working out. So we are burning anything that we can find. We are burning wood and many other things. So they are all, we call them fossil fuels. So we consume or we burn fossil fuels to provide, to supply the energy of our society. So this chart is showing what energy types we are now using. Oil is about 26%, natural gas 32%, coal 17%. So we have only renewables here 2.7%, hydroelectric power is about 3.9%. So as you see, almost about 90% of consumption is based on fossil fuels. So we are burning fossil fuels to supply the energy needs of the societies. So it means that we are emitting a lot of carbon dioxide into the atmosphere, and the atmosphere is getting warmer and warmer, and this is expected to lead in environmental problems, as we all know. Probably we are experiencing today the hurricanes, unexpected sudden changes in the climate, and all of these are being considered as a result of these climate change. So climate change is a big problem, and this will be even bigger problem in the near future. Okay? So we have to change this picture somehow. When we look at Turkish energy demand, when we look at Turkey, we see even more dramatic case. Turkey is using 1% of the whole energy consumption of the world, and 15% of that is the electricity production. And here, one of the striking features of Turkish energy consumption is that we are importing 75% of what we are consuming. So only 1/4 of the energy consumption is generated here in Turkey, and 75% is imported from the outside. And it is imported from by using, for instance, in 2012, we used 60 $60 billion US dollars to pay this energy to import. And this is creating a big problem in Turkish economy, as you know. So we have an environmental problem, but we have also the economical problem. And on top of these two, okay, if you look at this image, you see that the gas lines are coming from Russia through Black Sea and from Iran, from Azerbaijan. We have two main natural gas pipelines coming from Iran, Azerbaijan, and Russia, and also oil lines from northern Iran. They are all pumping fuels into Turkey. Some of them are exported further, but most of them are used in Turkey. So this is not a good picture, because in addition to the economical and environmental problems, we are very much depending on these three countries. So this is also kind of economical dependence, also political dependence at some level. So dependence on external resources creates a threat for the economical and political independence of Turkey. So we have a lot of problems related, connected to the energy issue of Turkey. But when we look at the energy resources in the available around us, we see that solar energy is far much more than all other energy resources. So this is comparing solar energy with coal, with uranium, and with, for instance, hydroelectricity. And this sphere is showing the total energy consumption of the world. So solar energy is this much. So we are receiving this much solar energy every year, 23,000 terawatt a year. We are only using 16, 17, or 18 terawatt a year. So it is thousands times more than all other resources. So solar energy is more than sufficient to provide any energy need that you might imagine in your life. Okay? So the problem is, of course, is to convert this energy, solar energy, to other resources, other sources, other types, like kinetic energy, like electricity, like heat, whatever. Okay? So solar energy is sufficient, and it will be the major primary energy resource in the future. So there is no doubt about it. I have no doubt about it. So in, let's say, 50 years from now, solar energy will be the main primary energy resource that we will be using on our planet. Okay? So when we look at the potential around us, solar energy potential, Turkey is in a very good position. Together with Spain and Italy, we have very nice solar irradiation. We receive quite much solar energy in the southern Turkey, like southern Spain, okay, compared to other European countries. So there are some numbers here, but I don't want to now explain all of them. But just to compare, for instance, with Germany, you see we have quite much energy compared to Germany. And Germany is the leading country now in the solar energy usage. Today, the biggest power plants or the largest usage of solar energy is in Germany. Okay, so if Germany is using this much solar energy with so less solar radiation, so we should be doing much more than that. Okay, we should benefit solar energy much more than what Germany is. Okay. So I'd say that's a good comparison. So this is enough for the economy and the solar energy. And if you have any questions, Jack, so I can be very happy to answer. For instance, today there are power stations with the power of 600 megawatt, 500 megawatt, and there are applications, very small applications, big applications. So it's a very flexible system, solar energy systems. you can use in your watches, in your calculators, but you can also make very big power stations by using these solar modules. So this is very convenient. It doesn't have any moving part. It is very silent. Doesn't generate any sound. Okay, it converts the energy directly from radiation into electricity. It's not like the other conventional systems. For instance, in a hydroelectric power station or in a nuclear power station, you have to generate steam, and that steam rotates turbines to generate electricity. So you have a lot of processes taking place to generate electricity. But here, you have an electronic device, which we call it solar cell. Okay, the solar cell converts the energy, incoming energy, directly to the electricity without any without any chemical mechanical process. It's a dry process, and it doesn't need any fuel. It doesn't need any maintenance. So a solar module can be used up to 30 years, 35 years without any significant problem. Okay, so solar energy is very convenient and very peaceful and very environmentally friendly. So we have almost no choice in future for our country. Any question here? No? Okay, so from now on, I would like to give you some information about UNAM. UNAM was founded 2009. Okay. The main mission is to develop fundamental knowledge and methodology to fabricate state-of-the-art solar energy conversion system. This is our main mission. So we are a technology center. We are not a center for applications. Okay? Sometimes people are confusing because there are many research centers in Turkey. Many of them are dealing with applications rather than technology development. But like other centers in our university, this is the mission of our university, to develop new knowledge, new methodology, and new technologies. Okay? So our mission is to develop solar energy conversion systems. Of course, we are willing to collaborate, contribute, and create synergy with all institutions, individuals, students, at national level and international level. Okay. And training and education is our main activity of research. Okay, we created UNAM beginning of 2009. Okay, of course, based on the research experience that we had already in our university. Our university has always been a pioneering university in many fields, including solar energy. The first solar house was built here on our campus in 1970s. You might have seen that. It's next to the management faculty. Just on the way from preparatory school. There's a small house that was built in 1970s as a solar house. Okay? It is very old one, but it's still being used. Okay? And later in 1980s, work studies started on development of photovoltaic solar cells here. We have applications dating back to 1980s, 1990s. So we had already certain tradition and experience on photovoltaic systems. But in 2009, we made a jump. Okay, so we applied the Ministry of Development at that time, and we got a big project. Okay, and we got money to create laboratories, infrastructure for this type of research, and then we created a lot of laboratories. So I recommend you to visit our laboratories. They are open to everybody, so you can always come and see our laboratories. We have several labs. I will show them to you. Today, UNAM is the leading national center on solar energy research and applications. in terms of technology development. So here are our labs. Our main facility is under this building in the basement area. So we have crystalline silicon solar cell lab, amorphous silicon solar cell lab, cadmium telluride, copper medium gallium ceramic titanium solar cell lab. We have outdoor facility on top of our building. There is an organic solar cell lab, which is very well developed lab at the chemistry department. And dye synthesized solar cell lab, led by Professor Zembash at material engineering department. And with mechanical engineering, we are currently developing a lab on solar thermal electricity, led by Dr. Director. Of course, all of these structures are utilizing somehow other research centers and other centers in the university. Central lab is supporting us very effectively in many different projects, and lab center, quantum lab, they are all interacting with us. So we are always collaborating with them when necessary, when needed. And we hope and we are sure that we will be moving into a new building. Okay? Sometimes called snake story, but it's okay. It has been a long time. This project started 2 years ago, but it's about to be realized now. A new building will be constructed here on our campus. It will be called Venture Research Park. And we'll have a large area there, large lab space in one part of this building. Here is showing the human potential. We have a management board, and here is showing the active faculty members that are working with us from physics department, chemistry, material science, metallurgical engineering department, chemical engineering department, mechanical engineering, and MIT department. So all these faculty members are somehow doing something with us. Maybe not 100%. They are spending some time with our center, or their students are using our infrastructure. So the number of students, about 60 right now. Again, they are not maybe doing all of their works at our labs, but they are using some part of our facilities in their studies. So graduate students are heavily using our facilities. So we have permanent engineers provided by the university administration. This is very important. We have always been supported by the university administration through the years, and we have received some staff members to support our infrastructure. And also we have some administrative staff. Okay. So we are moving towards a kind of institutional structure. Yeah. But we are well connected to Europe. We are well known in Europe right now. We are part of some European organizations like the Energy Platform, like the Energy Alliance. We are currently running 2 major projects under the 7th Framework Program, and 2 others again are being administrated by us from the 7th program. And more projects are to come. I mean, we are now applying preparing new proposals for the European program. So we are well aware of European support programs, and part of them in the last, let's say, 5 years that we are existing. Okay, let me show you some slides from our labs. This is the crystalline silicon solar cell lab. It's a clean room. This is why we are using such special clothes there. They're covering the head. except me. You see, I don't have hair, so I don't need to cover my head. So. Or so, you see, but this guy is should be covered somehow. But anyway, this is a clean room. It has 10,000 class cleanness. It is designed specifically for photovoltaic solar cell development. It's not a general clean room, so it's not meant to serve other research fields. It is specifically designed for photovoltaic solar cell development. Probably these are my hands holding a solar cell that we fabricated. This is an industry-sized solar cell. It's 15 centimeters by 15 centimeters. And this is the only place in Turkey where you can fabricate such solar cells. Industry is very much interested in this. Okay? Because in the normal solar modules now today, available in the market, commercial market, they are all using these type of solar cells. Okay, this is the entrance of the furnace oven that we use to make these solar cells, and you see these wafers. These are silicon wafers. They're very thin wafers. They are the thickness is about 200 micrometers. Okay, we can put 50 of them at a time into the furnace to do a kind of chemical process for the solar cell production. Now here is showing the some results. This is, we call it monocrystalline silicon solar cell. This one is multicrystalline silicon solar cell. Both of them are available today in the commercial market. And in the market, almost 50-50 market share. And in the monocrystalline cell, you see the color is same everywhere. It is very uniform. There is no color variation because the structure of this wafer is same everywhere with the same crystalline orientation, the same regular positioning of the atoms. So there is no orientational difference from this point to this point between atoms. It's a perfect structure, amazing. I mean, you have large area, you have trillions of atoms altogether, but they are in crystalline form and their position are exactly the same place with respect to each other. So fully symmetrical single crystalline structure. And this can be done at industrial level. I mean that you can produce millions of them with the same property without any significant variation. Okay, in the case of multicrystalline cell, you see some color variations, which is showing the differences in the orientational dependence. Here you have different crystal domains. The material is the same. There is no difference in the material between domains, but the crystal orientation is different, so that the interaction with the light has differences. So you see, you have different reflection from the surface. For this reason, even though the material is the same, you see different material, different colors on your surface. Okay. Sorry. Yes.
What is the main difference in application for two?
Say again.
What is the main differences in applications for monocrystalline?
Okay, good question.
Which one is more efficient?
Okay. Well, monocrystalline silicon is a better material. You can guess, I mean, it's more uniform. This is a better material. This is a lower quality material. This has a higher efficiency, generates more electricity. This generates less electricity. However, this is more expensive than this one. At the end of the day, the price of the electricity that you generate is almost the same. Okay? This has lower efficiency, but cheaper cost, material cost. This is higher efficiency, but higher material cost. So, I mean, roughly the same. Sometimes this depends on little bit on the financial situation in this sector. Sometimes people are using this one because it is more, it is cheaper than the other, and more cheaper than the other, and you get more better as an industrial person, for instance. But they are roughly the same. Like sometimes 1 year this is sold more than this one, another year this is more preferred than the other. Well, here it is. Okay, you can fit this. This is the one that we fabricated in our lab. Yeah. This is the industrial size solar cell. Well, when you look at the cross section of this material, just look at from this side, what you see that you have different levels, different material structures. And from this orange point, from this interface up to here, it's silicon crystal. We have different colors because we have processed them differently. In this orange color means that we have N-type silicon, meaning that I have put phosphor atoms into that region. I have doped it, and I added this chemical species into the surface. So I made it N-type, we call it N-type. And when it is P-type, it means that it contains a lot of boron atoms. Okay. So this part of silicon is doped with phosphorus, and this part of silicon is doped with boron atoms. And in that way, you create so-called p-n junction. P-n junction is the fundamental device structure in microelectronics today, not only in PV. All integrated circuits, all electronic components, and your computers, remote controls, cell phones, they have all integrated circuits, and they are all based on p-n junction. Okay? We can today make computer central processing unit, Intel is making these units, because we are able to make these p-n junctions. Everything has started from this process. Okay? And it started in 1947, the first transistor was discovered. Okay? And later on it was discovered that the same p-n junction acts as a solar cell. It generates electricity when you expose it to the solar radiation. Okay? This is the current voltage characteristics of the solar cell that we fabricated here in our facility. Okay? So you see the current, and here is the voltage. Vertical axis is current, horizontal axis is the voltage. So when the voltage is zero, you generate a current. Okay? So it means that you extract power from this. So there is no voltage, but you obtain the current. And you might probably know that power is equal to I times V. Okay? So if you multiply the current with the voltage, you obtain power. Okay? If you multiply I times V, you can find out how much power you can get from this cell. Okay? And there is a maximum point somewhere where you get the maximum power extraction from this generators. You can call it generator as you wish. Okay? So a cell like this one, like you are holding, can generate about 4 watts. In one solar cell can generate 4 watts. So you can combine them together to get more power. And today, as I mentioned at the beginning, there are power stations generating a power of 500 megawatt. Okay? So you can calculate how many of these pieces are used in such a big power station. It's a huge amount. Okay? So you see the efficiency is the conversion efficiency is about 18% for our solar cell. Today there are cells available up to efficiencies about 21, 22, okay, using different technologies. And efficiency is equal to the output power that you generate, electrical power, divided by the input power that you feed into the cell. Okay. So it says 20%, approximately 20%. It means that if you receive 1,000 watt from the sun per square meter, you can generate about 200 watt from 1 square meter. So you can calculate how much area you might need to set up our system on the roof of your building, for instance. Well, we have demonstrated different modules. We call them modules, sometimes we call them panel. They are the same. These modules, we made them just to demonstrate. Okay, this is not, we don't do any research in the module production. We are focused on cell production, cell development. But for general public, for journalists, politicians, we always generate some, make some demonstration systems so that we can get more support from them. Okay. But, of course, as a university, as a scientific research center, you should always do fundamental research. Okay? Without fundamental research, you can never reach a better product. Okay? Sometimes this is not seen by the people, especially by the politicians and journalists. Better products can only be generated if you are doing fundamental research. Okay? So this is one example that we have been doing. In this study, we used we coat the surface of the cells with nanowires. Okay, nanotechnology is the popular word today among scientific community. Okay? So we try to use nanowires on the surface of the solar cell to reduce the reflection. Okay, so we would like to reduce the reflection from the surface because we want to keep most of the light inside the device so that we can generate more power. Okay, so here it is showing the standard cells, multicrystalline and monocrystalline. Here is showing the cells with nanowires, and this is published recently in the Journal of Photovoltaics. So if you look at the surface of this cell, you will see that under microscope, under electron microscope, you see that the surface has a lot of very tiny nanowires with the diameter of a few, maybe 100 nanometers or 60 nanometers. Okay? So the length of the wires can be adjusted, the thickness can be, to some extent, can be adjusted and so on. So in this way, you see our cells are looking quite black. So it means that there is no reflection, almost no reflection from the surface. So it means that with this technique, we have reduced the reflection to below the industrial standard. So I have also got this one here. It's the same cell, but we have nanowires on the surface. You cannot see them, but you can see from the color.
Is it possible to build some pyramidal structures on this?
Yeah, that is something that we are routinely doing. Yeah, normally in the cell, normally it has these pyramids on the surface. This is standard industrial technique, but we are looking for something maybe going beyond this pyramids performance. Okay. Well, this is an example from our fundamental research. There are many such research, so I don't have time to mention all of them, but we are doing several other things in this direction. Okay, the second laboratory is the thin film silicon solar cell research lab. In here we have a big cluster system, plasma system. This is built by a Turkish company, by the way. So we,
May I ask you, where is the output of this thing?
sorry?
Output of this thing?
Out-
Where do we obtain it?
Oh, output, yeah, yes, of course. I mean, this is the cell. Okay. This is actually one diode only. The voltage of this that you can generate is about 0.6 electron volt. Yes. 0.6 volts. Sorry. And you take one contact from this side, the other contact from the back side. Okay. It's a single diode that you might see in the electronic circuits. In the electronic circuits, the diodes have very small dimensions, very tiny ones. But here you need the area. Okay, you don't need to collect the radiation. So one connection from the front side, the other connection from the back side. Okay. And here's our logo, the Günam's logo. We print always our logo on the cells that we fabricate, because sometimes people may not be leaving us. This can be done in Turkey. So there's always our logo in our
The voltage
cells.
is the same on the surface everywhere? The voltage on the surface, is it the same for everywhere?
Cells, I mean, in a standard industry production line, the voltage of each cell is almost the same. It's about 625 millivolt or so. Well, in the case of thin film lab, we have this cluster PCB system in which we have 4 plasma chambers and 2 metallization chambers. And this system was designed by us with a Turkish company, and it was made here, made in Turkey. So it has that importance also. Okay, using this, we can make solar cell on glass substrate. This is a different type of cell. Okay. So you have glass, you make your PN junction using thin films on top of each other. So you put, here is your glass, you put different materials and material types on top of each other, you create a stack of materials so that you get the PN junction. Okay, and you get power. So here is showing the IV curve of this solar cell. It has a lower efficiency, it's about 3% efficiency, but it's large area, it's cheaper and so on. So thin film solar cells are supposed to be cheaper, and they have very large areas. They can be used as construction elements as well on the buildings. So it has several advantages and can be used in different applications. However, today for the energy generation, to making big power plants, the previous one for the energy generation, crystalline silicon cells are dominating the market. Almost 90% of the market is now dominated by the crystalline silicon source. Okay, so using these thin film systems, we have been able to make solar cells on glass substrate. Okay, and there's an outdoor test facility on top of this building. With an Ankara view, it's very nice view here. And here we are testing different products. These products are coming from either from Turkish companies, or European companies, or from universities, or from ourselves. And we are trying to make this outdoor test facility known across Europe. First of all, we would like to be a test point for the industry and research center in the future. So let me give you some information about other labs. Organic solar cell labs is led by Professor Topare and Ali Chipman. It's It's in chemistry department. Here's a picture from that lab. It is, this group is very active and one of the maybe best polymer scientists are in this group. They generate extremely very good publications, scientific publications. Some of them are being covered for the journals. So it is really very productive group. But organic solar cells are not suitable for the large-scale energy generation right now. They are good for small applications. Okay, dye-synthesized solar cell is led by Professor Zembaş in material science, metallurgical engineering department. Here, this is slightly different than organic cells, but it has some similarities with the organic solar cell system. Here, I will not give you the details how it works, but mainly it's a thin film system. It's cheaper, okay, and easy to fabricate. It's very convenient for flexible systems. For instance, a textile company located in Trakya region, that company is working with Professor Zembaş for the last 5 years. They are trying to make solar cells on clothes. That is their project, and that project is going quite well, and they are expecting to produce some commercial product in the near future. Okay. This is another system. It's not PV. It's not photovoltaic. Here, the sun radiation, solar radiation is focused on a pipe, as you see here, and there's a water flowing here, and water gets very hot and evaporated, and you get steam, and that steam can rotate turbines to generate electricity. This is called concentrated solar power. Professor Baker at Mechanical Engineering Department is the leading person in this study. And here is an example, an experimental system located on our northern Cyprus campus. And it is working now quite nicely, and they are doing some experiments with this system. And we are part of the European project in this field. And this thin film system, cadmium telluride, cadmium sulfide, and copper in cadmium selenide, they are also commercially today viable and available in the market. And this is one of the oldest topics that we are working in our department. This is a picture from 1997, almost 20 years ago. We published papers on this system. Okay, this Professor Parlak is still working on that. Professor Raşit, although she's vice rector of the university, she's trying to find some time to experiment with her students. And Professor Menelan at Material Science Department, he is interested in and he is focusing on nanomaterials. And many different nanomaterials, but this nanowire project was carried out together with him. So he was one of the scientists who first generated these nanowires on silicon surface. So we made very nice cells using those nanowires, and we show that the cells are working quite nicely, even though you have quite different structure on the cell surface. This is the Venture logo made by silicon nanowires and taken by an electron microscope. Okay, our test laboratories are unique in Turkey. We have many different test systems for photovoltaic solar cells as well as thermal solar cell systems. I'm not going to give you the details, but we have almost all necessary equipment to test a solar cell, both structurally and electronically and optically. So here is a picture that I like very much. And this picture was taken by one of our graduates. He's not in Turkey right now. He's a photographer. He's a very good photographer. So he took this picture for us and showing our family. Okay, maybe I should mention a few more things. One of them is the project that we have just started. This project is called MİGES. MİGES means Milli Güneş Enerjisi Santrali. This is a big national project supported by TURAN 1007 program and supported by the Ministry of Energy and Ministry of Food and Agriculture. And there are 3 partners in this project: TURAN and UNAM and a company, Raşit Energy, which is located in southwestern Turkey, Denizli. And the aim of this project is to create an infrastructure for the cell production in Turkey, which is not available right now. It's a huge project and it has a very large budget. And the company will invest on cell production. As one of the outputs of the project will be a power station in Ceylanpınar, in Urfa, city of Urfa. Ceylanpınar is still our border at that time in 2 years. So we will set up this 10 megawatt power station. 10 megawatt power station means we will be using 2.5 million such cells, and all those cells will be fabricated in Turkey. And almost 60% of the power station will be produced here in Turkey, made in Turkey. Okay? And my final announcement is a conference that we are organizing here. End of April, okay? And end of April, this is Solar TR3, which is the major scientific conference of solar energy in Turkey. And all these companies and institutions are supporting us, including Fraunhofer, Germany, Aselsan, Şişecam, and many others. So it will be a very big and nice conference, so you are all invited to attend this conference. So thank you for your attention. Say, if you have any questions, please ask.
Is it not possible to generate more than 0.6?
Sure, you can do that, but you need to use other materials, not silicon. There is a concept, we call it multi-junctional system. In that case, you can put several junctions on top of each other. And there is a very successful example based on another semiconductor, not silicon. In those cases, you can get up to 2 volts across the source.
But change the power, is the power the same?
No, the power will be higher. Okay, you get, the efficiency is about 44%. It's much higher than this one. It's about twice as much as this efficiency. But there are other problems with the system. It's not widely used right now because of the economic equation. It's very expensive. It's used only in satellites. Any other question?
As far as I see you only use silicon and solar cells. What is the main reason for these applications? What is the property of silicon and in using in the solar cells?
There is no other better material.
What's the main
Silicon is a miracle material. And silicon is the basic material for microelectronics. It's the main material for MEMS applications. I mean, silicon is a miracle, an excellent material. It has very good electrical properties, very good mechanical properties. It's very robust. It's very available. I mean, almost 25% of the Earth's crust is made of silicon. So you made it from sand. You might know. I mean, you extract silicon from sand. So it's available. It's abundant. So many reasons. But of course, for instance, a semiconductor like gallium arsenide, which is a compound semiconductor, gallium arsenide has better properties, better electronic properties, better optical properties. But it's not easy to do that. I mean, you cannot make such large gallium arsenide, so you can make only small pieces, so that is not sufficient for a PV application. Any other question? Okay, thank you.
Thank you very much for joining us. Science tree of matter.
Okay, thank you very much. Teşekkür ederim.